So now let's try to construct the follow sets for our simple example grammar here. So the follow set of our start symbol is simple because our start symbol needs to describe a grammar that can match all the input. So after we've resolved our start symbol, so we ended up recursively up here again, there are no more characters allowed in the input, because if there were, our grammar wouldn't be complete. So follow of S is what we indicate as $ here, the end of the input. Now let's take a look at follow of B. So the first rule where B appears is the first rule here. So S derives U, non-terminal B, non-terminal D, Z. And here, for our first rule, we can go down and use the first production here. So from non-terminal B, we resolve non-terminal B and terminal symbol V. And then we have something else. For example, we go up again here and say we have D and Z. So we have this here, U, B, V, D, Z. And it doesn't really matter that there's more non-terminals, because we know there's one terminal symbol to the right of B. So we can appear as one of the follow terminal symbols following our non-terminal B. And now we can go through all the possible combinations here. So again, we start with U, B, D, Z here. And then we go down this track here and say we can go to U, B, and derive EF from D. So we first resolve D here to EF. Then we can eliminate our E again using the epsilon as we've seen. So we have U, B, F, Z. And then we can resolve our F to an X. So we can finally have UB, and the resolved D would give us an X, and then our Z at the end. So X is another terminal symbol that can show up after B in such a production here. And we'll continue with the other ones here. So we go down that way again, but now instead of resolving EF by resolving E to epsilon, we resolve E to Y. And so we come to this one here, U, B, Y, F, Z. So Y is one of the other follow characters for our non-terminal symbol B. And the final one we get by going through this route E, B, E, F again. And then we can also resolve E by an epsilon, as well as F, which also resolves to an epsilon. So this D just resolves to 2 epsilons, so we read no single input character for all of D. So U, B, Z would be the last production here, which is resolved. So Z can also be a follow character for our non-terminal symbol B. And then we've finally gone through all the possibilities of resolving B, which is fine. So we're done, and we have this follow set for B here. So what are the other follow sets? Follow set for D. Well, when we resolve D, it can be, let's go down here, E and F. And whatever we do, we can use an epsilon here, and then we would end up just having that Z from U, B, D, Z here, because that's the only symbol that can actually appear to the right of D, right? Because there's no other production having D on the right-hand side, so that's the only option we have. Follow of E, you need to construct again by taking a closer look. So E can be, either resolved here this way by U, B, D, Z going to U, B, E, F, Z, and then if we still have the E here, we can either have the X by resolving the following F here to an X, or if we resolve this F to an epsilon again, then we would finally derive U, B, E, Z, because we've derived the D to E, the F to epsilon, and then after our E, we have a Z here. So the follow set for E is X and Z, and the follow set for F is simply Z, because we go from D to EF, and the F, whatever it is after the F, that's the final symbol of non-terminal symbol in deriving D. After that, we only have a Z left. So that's the sequence of derivations here. So what we did now, we have the first sets and we have the follow sets for our grammar. One thing that's also important is a property of a non-terminal symbol that we call nullable. So a non-terminal is nullable if it can produce in an arbitrary number of steps just the empty string. So if you take a look at different textbooks, you might find out that the notation actually is different between the books. So there's this one standard compiler's book, the so-called Dragon Book by Ahu, Ullman, Sethi, and Lamb, which is always mentioned first, I think, still when people do compiler courses, but we've decided to use a more modern approach with our textbook. So the Ahu, Ullman, Sethi, Lamb, the Dragon Book, denotes this property of nullability by putting an epsilon in the first set. What we do here is we denote this property that a non-terminal symbol can be. You can just derive an epsilon by keeping it in a separate record. So let's see, is our non-terminal symbol S nullable? No, because its only production here has terminal symbols, so it's not nullable. It always produces at least something. B, again, is also not nullable because it has two productions, but both productions include a terminal symbol. Is E nullable? Well, yes, because, well, there is one production that just produces epsilon for E, so it's nullable. Is F nullable? Same as before, of course, because there's production generating an epsilon. So the remaining question is if D is nullable, and you can see D resolves to E and F. E can be epsilon, F can also be epsilon, so we can have a resolution here that derives epsilon epsilon from D going through E and F, so D would in total resolve to an epsilon, so it's nullable again. So now we need to build the parsing table. And we do this obviously by obtaining the first and follow sets and also the nullability information for our grammar. And then we take a look at every production. X derives an alpha, so we've seen alphas are the combinations of terminal and non-terminal symbols. And then we try to apply two rules. So first, we enter this production X derives alpha at a part in our table, or location in our table, xt, where this character t, so for terminal symbol, for our production x, is in the first set of alpha. So this means we try to match the first character t here to this production here. So we actually try to see if it fits in. And if we have something like alpha goes to something with an epsilon, then we enter the production x derives alpha at the point xt, where t is actually in the follow set of our non-terminal symbol x. Now, this is simpler for an example, so let's enter all the rules for an example here. So here we have all the characters, the terminal symbols that might show up, u, v, w, or the other way around, u, w, v, x, y, z. And we know, well, when we have an S and our first character is a U, we enter production here, so we go from S to U, non-terminal B, non-terminal D, and a Z. And let's take a look at the productions for D. So D can have an X at the beginning. It would always go to E, F, or it can have a Y, so the other of its first characters, so it would go to E, F. For E, we have this one production here, and for F, we have the production going to X. Now what's happening for B? So we've already seen there's something in B which we've already noticed is problematic, this left recursion here. So B, when reading a W, it can either resolve this to just a W, or it can resolve this to going to B and putting a V at the end, because this W can appear arbitrary many times to the left. So this will not work because this table is not unambiguous. So if we try to expand B on our look-ahead W, this would again require a choice that our parser cannot make because it doesn't have unlimited look-ahead to our input token stream. So we need to change something in our table. What are we changing? Well, we're doing left recursion elimination. So our problematic rule is the rule deriving something from our non-terminal symbol B. And as we've seen already in eliminating left recursion, we add an additional rule B prime. So from B, now we first generate our non-terminal W on the left, and then we expand it to the right using B prime. and b prime can have as many v's as we want, and the epsilon to finish going recursively through b prime. So now, after we did this, we need to update the first follow and nullable sets, because we have another production here. So first of b, we now know, is always a w, because it's only one rule that starts with a w. Follow of b can be x, y, or z. b is not nullable. And for b prime, we have to now determine the first set. That's easy, because either it's epsilon, so it doesn't derive anything, or it's terminal symbol v and another b prime recursively. So our first set is just the terminal symbol v, and our follow set is again x, y, z here. So because we do go through d and can derive an x or y or this z here, and we've seen b prime can directly resolve to epsilon, so it's nullable. So now we need to add something to our table and to change the entry for b. So now we have a unique production we can choose whenever we have a w at the input for b. We can choose this new rule, b resolves to w b prime, and for b prime, when reading a v, we can go using the first production here, going from b prime, consuming a v, and recursively going into b prime again, and leave the rest of the table unchanged. So that was applying rule 1. Applying rule 2 means that whenever a non-terminal symbol is nullable, we need to insert this at the follow sets. So essentially what we have here is we need to add these productions here at the follow sets. So if we have one of these characters here in our follow set, we add the production going to epsilon here, and these productions here, here. And for d, we need to go to d to ef, because there's no other production, but we know it can ultimately lead just to an epsilon. So when we want to go through our table, we just start at our start symbol here, then we derive the first rule, and then we can recursively go through our list of non-terminal symbols and try to resolve all the open things that are in our input in our grammar. So what happens if we have something else as an input, like we start with reading a w or a y or a z? Well, that's invalid, so all the empty fields here denote that there is no match, so we cannot continue parsing, so that's an error. So the result of our approach here is that we've produced a parse table for an LL1 parser that contains only one rule to choose when we have a given combination of a non-terminal and a terminal symbol. This means that the parse tree can be built deterministically by following the method from our first example here. So first we pick productions for non-terminal symbols by looking them up in the table. And as we've just seen, if there's a combination without a production, that's an error. This L1 parse table can, of course, also be constructed by an algorithm, and this algorithm parses the input grammar. So we have the grammar as a textual description, and we can write something that uses scanning and parsing techniques again to derive this LL1 parse table. If you want to take a closer look, take a look at this reference here for the algorithm, but please note this book adds the set first plus to simplify the notation here. And this is the first step to create a parser generator. And because this parser generator just uses compilation techniques, so scanning and parsing again, because we parse our grammar here, this is also called a compiler. And we'll take a look at using one of these compilers, the so-called YAC compiler, which just stands for yet another compiler. So you've seen there have been several others before, but YAC is one of the standard tools in Unix. So we'll use this for building our compiler. But before we can do this, we'll take a look at other methods to construct parsers, bottom-up parsers, in the next lecture. So what we know is that we can express most of our programming language constructs. We've seen if and while loops, for example, in such a backtrack-free grammar. So we actually only need a bit of look ahead, and then we can decide just using the table how to proceed. And these predictive parsers we can generate or write are simple, they're compact and efficient. We can implement them in a different number of ways. We can use them hand-coded recursive descent parsers, or we can use actually the same approach, just having it generated as an LL1 parser. We can have this L1 parser table-driven, or we can even build a direct-coded L1 parser. The primary drawback of such a top-down predictive parser is that they cannot handle left recursions. So left recursive grammars, as we've seen, model the left-to-right associativity of expression operators more naturally than a right recursive grammar would do. So if we have an arithmetic expression 2 plus 3 plus 4 or whatever, then the associativity would be easier to parse if we would just use a left recursive grammar, but we can always rewrite them to something else that's no longer left recursive. So what lies ahead now is more parsing. We're looking at a different approach to do parsing now from the bottom up. So our input stream drives the decisions instead of that our grammar drives what we need to expect from our input stream. And these are so-called LR1 parsers. And these are the basis for many commercial parser generators. For example, the YAC or GNU version of it, Bison parsers, I've just mentioned. So these use a bit more complex approach, as we'll see in the next lecture. So here's a list of references for this lecture. If you want to dig deeper, you're always welcome to do this. So Aho and Ullman, two of the authors of this Dragon Compilers book, wrote a paper on deterministic parsing of ambiguous grammars already in 1975. There's a paper for properties of deterministic top-down grammars, which is even older. This book by Nicholas Wirth on compiler construction, the 27 edition, is freely available there. It's a bit more than 100 pages. It's written in a language you might not be familiar with, but it generates a complete small compiler for a subset in the newest edition for the Oberon language. It's rather implementation-oriented, so don't expect too much theoretical detail, which is fine with me. But of course, the language it just uses is a bit restricted. Then, of course, we have our textbook here by Cooper and Thorson, Engineering a Compiler. They use this first plus set. We've omitted this. They use it for just trying to simplify some of their expressions. So there's lots of theory included, which we didn't discuss in the lecture. But again, you're welcome to dig deeper here. And finally, of course, the reference to the standard Dragon book, the Compiler's Principal Techniques and Tools book, which is a standard book, which you can use as additional literature if you like, to always get some more background information or just to find a different way to express things. So that's our Compilers lecture for today. Thanks for listening, and until next time.